Hello, and welcome to this blockchain security course. So before we dive into it, quick overview of what we'll be talking about in this module. We'll start out with an introduction to the blockchain, and then discuss how the blockchain works at each level. So we'll talk about blockchain transactions, blockchain's blocks and chains that it gets its name from, the blockchain node, and the peer-to-peer network that links blockchain nodes together. And then after that, we'll discuss some of the core features of blockchain technology. And so let's get started. So what is the blockchain? So the blockchain is designed to create a decentralized, immutable digital ledger. And so what this means is that we're using technology that differs very significantly from traditional ways of doing things. So in the past, if you want to implement, say, a financial system, like a bank, then you're relying on some form of centralized party to maintain the integrity and correctness of the accounts ledger. So for example, you might have a bank account with money in it, and you can perform transfers between those bank accounts. So you might send money directly to another bank account via an ACH or wire transfer. You might withdraw money from that account using credit, debit card, check, an ATM, etc. You might put money into the bank account, again, using ATM or a teller in a bank. All of these affect the balance of value in your account, how much money you have deposited. And the bank's responsible for tracking that information. So they make sure that your account balance is updated based off of deposits and withdrawals, etc. And they also manage the integrity of that ledger. So they might have dispute resolution processes. They make sure that no unauthorized changes can be made to your account, etc. And so all of this financial system is based on the assumption that you trust your bank, that the value in your account, where you're transferring something that holds some level of value, like fiat currency, into a number in the ledger, that value in that ledger will be appropriately maintained and tracked throughout your relationship with the bank. That the bank won't just simply decide one day, well, you had X amount of money in your account and now you don't anymore. We've gotten rid of it. Because all it is a number in a database. And so that requires a certain amount of trust in this centralized party. Also, bank ledgers are mutable, or they can be changed at some level arbitrarily by the financial institution. I mean, there are rules and regulations governing what they can do. But for example, if your credit card is stolen, then the transactions performed using that card can be undone if they're found to be illegitimate. And so that has its benefits, but it also has its downsides, because authorized changes can be undone as well if it's determined to be invalid, etc. And so with traditional financial systems, you're relying on a centralized authority to essentially make sure the system works like it's supposed to. Blockchain eliminates that centralized authority. Instead of a single bank or financial institution managing your money, the ledger that tracks your account balance is distributed and decentralized. Each node in the blockchain network keeps a copy, updates it, etc. And we have rules that are based off of protocols, cryptographic algorithms, etc., that ensure that everyone plays by the rules and that the balance in your account is accurate. And so to do this, we have a complex and multi-layered system. A blockchain is complicated because it not only needs to have mechanisms for storing and maintaining the digital ledger, it also needs to have mechanisms for securing it. And so with the complexity of the blockchain system comes complexity of blockchain security. So if you've got a complex system, making sure it does what it's supposed to do, especially when you don't have a centralized authority, can be tough. And in the blockchain, the stakes of failure are high. So if there is a hack of a blockchain system, so maybe you've lost control of your private key and someone performs a transaction on your behalf. Or if you have smart contracts, like decentralized smart contracts, if those are hacked, that blockchain's ledger is designed to be immutable, meaning that transactions can't be reversed. And so if something goes wrong on the blockchain, it's really, really hard to the point of being pretty much impossible to have it undone. And so we need to make sure that things are secure and the attack never happens, rather than trying to fix it after the fact. And so to understand blockchain security, we need to understand the blockchain. You can't secure something you don't understand. And these blockchain environments are, as I mentioned, complex, multi-layered systems. We have underlying infrastructure that does all the work, the nodes and networks. We have an array of protocols that make sure everyone plays by the rules and implement certain systems. We have users interacting with the network. We have smart contracts running on top of the blockchain, etc. And so some key components of the blockchain system that we're going to talk about here to lay the groundwork for our discussion of blockchain security include data structures, so the transactions and the blocks that we use to create this essentially distributed and decentralized database, and then also the infrastructure, so the nodes and networks that make everything run. And so let's start by talking about the fundamental unit of data on the blockchain's ledger, the transaction. So data is stored on the blockchain in the form of transactions. So if you want to add data to the blockchain's ledger, you're going to be creating a transaction. And it gets its name from the fact that the original blockchains were storing literal transactions. So take Bitcoin. Bitcoin is the original blockchain. The Bitcoin white paper by Satoshi Nakamoto defined how blockchain works. And the goal of Bitcoin was to implement a distributed, decentralized financial system. So all of those transfers of value, deposits, withdrawals, etc., that you can do with a bank, you can also do on Bitcoin. The difference is centralized authority versus no centralized authority. And so in this decentralized financial system, you need the accounts ledger to show how much value is in each person's account, where that value is moving, etc. And that's the blockchain's ledger. And so each transaction on the blockchain indicates that value is coming from these places and going to these places. And so over time, that definition of transaction is stretched a little bit. So we don't only have financial transfers. When we have smart contract platforms like Ethereum, the transactions can hold executable code saying that in the world computer, the distributed virtual machine, which we'll talk about a lot more in a later module, that each node in the network should execute this code to update the state of the world computer. And so in either case, we have this fundamental unit of data storage on the blockchain. And the blockchain, or at least the original blockchains, were designed to be publicly accessible. So anyone can participate in the blockchain. You can create an account, generate transactions, etc. And this process is easy because identity management, account management on the blockchain is managed using public key cryptography. You generate a random private key. From that private key is derived a public key. And then from that public key is derived an account address. And so with your private key, you can create digital signatures associated with your particular account that validate that this particular transaction was authorized by someone with this account's private key. Once you've created that digital signature, that transaction can be broadcast to the rest of the blockchain network. And so as we see here, a transaction might not be a single transfer of value from one point to another. There's the potential that you might have multiple sources of value and multiple destinations of value within the same transaction. And then, as I mentioned, smart contracts might not even be focused on transactions, instead having executable code within these transactions. However, we've got this fundamental unit of data which we're going to be storing on the blockchain ledger. However, these transactions aren't individually and immediately added to the ledger. Instead, we have blocks, which are the fundamental unit of data that's actually added to the ledger. So a transaction is something that can be created by a particular account and is data that they want to be added to the ledger. Those transactions are collected into blocks, and each block is added to the ledger as part of the update process. And so individual transactions aren't added, they're added as part of blocks. And these blocks are created at regular or near regular intervals by block producers. And so these are nodes that participate in the consensus algorithm of the blockchain and are responsible for essentially creating the blobs of data that are used to update the blockchain ledger. And so these blocks have two main parts. There's a block header and a block body. And so the block header contains metadata about the block. So this could include timestamps. It includes the root hash of a Merkle tree, more on that later, that summarizes transactions. It can include a nonce value for proof of work, and it also includes the hash of the previous block header in the chain. And so this is the chain of blockchain. And these are what help preserve the immutability of the blockchain's digital ledger. Creating a single block is easy because block producers do it all the time and at regular intervals. For example, Bitcoin blocks are created every 10 minutes, give or take. And they don't even take that long to create. There's processes for making sure that a block is actually valid that makes it take that long. And so if it's easy to create a valid block, then it's relatively easy to create a fake version of a valid block or a contradictory one. So you could have two different versions of the same block that have different transactions in them. And some of those transactions might be mutually contradictory. For example, a double spend could be Alice sending 5 Bitcoin to Bob in one version of a transaction and sending the same 5 Bitcoin to Charlie in another version. Both of those can't exist because they're spending the same money. And so we can't have double spends on the blockchain, and we want to make sure that we can't rewrite the history of the ledger. And so the fact that a single block is easy to rebuild is good because we need to be able to create blocks, but the chains that link blocks together into a coherent whole are designed to ensure that creating multiple fake blocks, which would be necessary to attack the blockchain, is hard. And we'll talk more about why this is later in the course. The other part of a blockchain block is the block body. And so this is simply just the set of transactions contained within the block. And so the Merkle tree I mentioned a couple minutes ago securely summarizes these transactions into a single value, that Merkle tree transaction root. And that root of the tree is included in the header hash for the blockchains. And so the immutability protection of the header that it gets from these blocks and chains flows down to the transactions in the block body as well. And so that's how we make sure that no one can swap out transactions on the blockchain's ledger. And so those two concepts, the transaction and the block, are data structures in blockchain. And that's more on the theory or the protocol side of the blockchain. However, we also have the infrastructure side. So something like the Bitcoin white paper defines the theory of how blockchain works, but to be useful, it has to be actually implemented in some way. And so how we implement it is using traditional computers and networks. And so the blockchain node is a name for a computer that's helping to support and run the blockchain. And a blockchain node can have multiple different roles that it fulfills within the blockchain. This includes block production, so creating blocks. Part of this is participating in the consensus algorithm, which helps select the block producer and ensure that the blockchain network all agrees on what transactions are included in each block and what the current state of the digital ledger is. We also have the storage of the digital ledger. So the whole point of blockchain is to maintain an accounts ledger of the history of the network. And so each node in the network might participate in storing that ledger. And so it's important to note that not all nodes will perform all of these duties. So for example, you might have producing nodes which create blocks. And so they'll participate in consensus, they'll build blocks, send them to the rest of the network, etc. You might also have non-producing nodes, which don't. However, they might still store a copy of the blockchain's digital ledger or perform other helpful functions that help the network to work. And so a blockchain node is essentially just a computer running software that helps make the blockchain possible because we don't have some centralized authority responsible for doing all the work of maintaining our accounts ledger. And so we need a network of nodes to actually maintain the blockchain. And all of these nodes need to be able to talk to each other, which is where the peer-to-peer network comes into play. So blockchain is very decentralization focused, meaning it doesn't want any central authority or single point of failure. So that helps protect against misuse of power, and it also provides a greater level of resiliency against attack or other disruptive events. And so traditional client-server network models aren't used in blockchain because that server, so something like the Gmail server when you're sending emails, where if you're sending an email, I'd send it to the server and it goes to you. Well, that server is a single point of failure, single point of authority, etc. And so blockchain decentralization tries to avoid that. And so it uses a peer-to-peer network where each node is directly connected to other nodes, or each user is directly connected to other users. And so you could have a fully connected network like the one we see in the image here, where every node is connected directly to everyone else, or at least some of these nodes are fully connected, like the bottom left corner. However, this sort of network isn't scalable because the number of connections grows with the square of the number of nodes. And so if you get to a network the size of Bitcoin or Ethereum, the number of connections you need quickly becomes infeasible. And so what blockchain uses is a not fully connected network where each node only has a few peers that it's directly connected to. And so if I want to send a transaction out to the blockchain network for inclusion in a future block, I'd send it to my peers, who'd send it to their peers, who'd send it to their peers, and so on. And so what this means is that data, such as transactions and blocks, propagate through the network through multiple different steps through each peer group. And so this creates multiple different paths for the data to travel through the network, which is good for resiliency and decentralization. And the data eventually gets to everyone. It's just not a direct hop through a centralized server. And so we've talked about how the blockchain works and how it's structured at a high level. We'll dive more into various aspects later in this course. But the unique design of the blockchain provides some certain core features or benefits that come from its decentralization, distribution, etc. So one of these benefits is anonymity. So the design of how blockchain identity management works means that there's a level of anonymity or pseudo-anonymity on the blockchain because blockchain accounts are not tied to real-world identities directly. So for example, to create a blockchain account, all you need to do is generate a valid private key from which you can calculate a valid public key from which you can calculate an account address, and you've got a valid account. Well, this private key that you generate first is a random number. And so there's no direct linkage between real-world identity and private key. And so there's a level of anonymity on the blockchain because without that linkage, you can't say with certainty that this account belongs to this person without further information. And that information might be available. If I want to receive a blockchain transaction, I need to give someone my address so that they can send that value to me. And so that conclusively links that account to my identity. You also have the potential for patterns of life. So if I'm using the blockchain for day-to-day life and using transactions to pay for things, if a particular blockchain account is seen to make transactions with my local cafe, supermarket, etc., then observing those transactions, you could find out that someone living near me owns this account, and it could be me. And so that helps to break the anonymity of blockchain, which is how law enforcement is able to track down people who misuse the technology. Another core feature or benefit of blockchain is decentralization. We've touched on this a couple times in this video. So instead of relying on a centralized authority to maintain the digital ledger, make sure it's correct, immutable, etc., we have a network of nodes that cooperate with one another under a set of rules which are backed up by various cryptographic protocols, algorithms, etc. So rather than putting trust in a particular authority to do things, it's a network where the trust is transferred to those algorithms instead. A third benefit of blockchain is fault tolerance. So if you have a centralized system, one where you're reliant on that centralized bank, financial institution, etc., to maintain the ledger, then that centralized institution is a single point of failure. If, for example, its database gets ransomware and they don't have backups or they don't have immediate access to backups, then operations might be disrupted, potentially indefinitely. If all of their data is encrypted and they can't get it back, then they've lost all of that data. Or if getting it back takes time, then there's a time in which those services can't be used. Or something as simple as their main data center has a power outage or loss of internet connectivity due to a thunderstorm. Then for that period of time, they could have degraded or completely destroyed functionality. And so that's because there are certain sections of the system that are single points of failure that are essential to its operations. Blockchain, you have a network of nodes that all participate, and none of them are essential by design. That's our decentralization. And so with this lack of essential parties, there's the fact that no node, if it goes down, brings the network down with it. And so you can lose many nodes in a blockchain network before it no longer becomes operational. You might lose some level of productivity, efficiency, and security if many nodes are brought offline, but the network will still function. Another core benefit of blockchain is the immutability of its digital ledger. So we touched on this briefly earlier in this module, where we talked about the blocks and chains and how each block header is linked together, making it hard to modify one without modifying the rest. We'll talk about this more later, but this makes it very hard for someone to rewrite the history of the blockchain. And this is a benefit because we don't have an official version of the blockchain's digital ledger. Each node in the network keeps its own copy, and we work really hard to make sure all those copies match. But those nodes have incentive to modify their copy. If there's a transaction in there where I send value to you, then if Alice is maintaining a node, Alice has incentive to rewrite that transaction so that I send value to her because she gets money. And so Bob, also running a node, would rewrite that transaction to send value to him, and so on and so forth. And so if we don't trust Alice and Bob not to rewrite the ledger, there's a potential for chaos, loss of consensus, and we don't have a trustworthy financial system. However, with the design of blockchain, the ledger's not easy to rewrite, and so we can safely ask Alice and Bob to store copies of the ledger and still trust those copies because there isn't a way for them to rewrite them to their benefit or to harm us. Another core feature of blockchain is transparency. So every node in the blockchain network has a copy of the digital ledger, and every node is responsible for validating every transaction in every block before adding that block to its copy of the digital ledger. And so what this means is that every node in the network has a certain level of insight into every transaction. They'll know the source, destination, and value, unless we're talking about a privacy coin like Monero. And this information allows them to make sure a transaction's valid. So before they're going to accept a transaction where Alice sends 5 Bitcoin to Bob, they want to make sure Alice actually has 5 Bitcoin to send. So that means they need to know the source of the transaction, so whose account to look at, and the value in that account. To know the value in that account, they need to know the destination of previous transactions. Alice's 5 Bitcoin had to come from somewhere, and so previous transaction destinations are necessary to validate a transaction. And so what this all boils down to is with many, many copies of the ledger and with certain parts of transaction data being visible, there's a level of transparency to the ledger. Everyone knows what's going on in the history of the blockchain. You can start at the Genesis block or the very first block of the blockchain, work through and know the value in every blockchain account and every transaction that any account has performed, unless there are cryptographic protocols that are used to conceal that information without breaking validation. However, even in that case, the level of transparency is much higher than, say, where nobody knows anything about what's going on inside, unless they're directly involved in a particular transaction. And then finally, the final benefit we'll talk about for blockchain here is trustlessness. So with a centralized financial institution, you need to trust them to not modify the ledger to their benefit, your harm, etc. So if I have an account with the bank and I have $500 in it, I'm trusting that that $500, which is essentially just a value in their database, remains there until I take it out. And that requires a level of trust, because they could easily delete that value and be like, I don't know what you're talking about. There's not $500 in that account. And so with blockchain, instead of trusting in this centralized authority to maintain the ledger, we've got a system of protocols, cryptographic algorithms, etc., that ensures that the ledger is correct, immutable, etc. So even though we have a bunch of nodes that are responsible for maintaining the ledger independently of one another, we don't need to trust any or all of those nodes, because there are algorithms in place that say that if a certain percentage of the nodes are honest, then the network will work even if some of them try to cheat the system. And the system is designed so that nodes are incentivized to behave properly. And so we should have that critical threshold of honest nodes, because it's more profitable to play fairly than to cheat. And so therefore we have a trustless system as well. And so before we close out this module, a quick recap of what we've discussed. We started out with an introduction to the blockchain, and essentially why we care about it, what it does for us. And we talked about how the blockchain works, including data structures like transactions and blocks, and the infrastructure like nodes and the peer-to-peer network. And then finally, we talked about some of the benefits that blockchain technology brings due to its unique structure. Thank you.